Hello, everyone. This is Mr. Smith. Glad to have you back. We're going to continue our talk of balancing chemical equations. This is a PowerPoint that I'll put up there in the play posit for you. But here we go. Here we have methane, CH4, with some oxygen that makes carbon dioxide and water. Now this type of reaction is combustion. But right now, we're not too concerned about that. We're just focusing on the same number of atoms going into a reaction, then coming out of the reaction. And so you can look at the circles, one black circle in, one black circle out, four red semicircles coming in, and then 1, 2, 3, 4 circles coming out, and red circles coming out, and then four hydrogens, 1, 2, 3, 4 going in, and four hydrogens coming out. But specifically, without looking at the actual circles and molecules, we can get that information from this equation here. And so we have, I guess, two different types of numbers. So here's a water molecule that you've seen for quite some time. And here's the formula, H2O. So what does this 2 refer to, the hydrogen or the oxygen? Well, it refers to the hydrogen, the element to the left of the number. As you can see, the two white circles there, those are the hydrogens. And so we call that a subscript. And again, that tells me how many of each atoms they have. Again, the elements to the left of the number. And then there's only one oxygen. The 1 is implied to be there. We don't write the 1. 0 is not really an option, so we write the 1. And so the other type of number, well, that would be the coefficient. So the coefficient goes in front of the molecule. And so what does that do to the H2O? Does it change it chemically? Does it change the formula? Does it change the colors? Does it change the elements? No, it just changes how many there are. And so instead of 1 water, now there's 2 water. And so what does that do? Well, now there's 1, 2, 3, 4 white hydrogens and 1, 2 red oxygens. So how does that look that way? Well, that's just distribution. So that 2 distributes to the subscripts. So now there are 4 hydrogens and now there are 2 oxygens. So that coefficient distributes to each of the subscripts in a formula. And so when you're looking at this, already balanced chemical reaction, you take inventory. On the left-hand side, you have 1 black carbon. You have 4 white hydrogens, 4 red oxygens. And again, you can just count those up, but you can see it here as well. There's the 1 carbon, there's the 4 hydrogens, and there's the 2 times 2 red oxygens. And on the other side, it is equal because it is balanced. And so we go ahead and count them up again. 1 black carbon, 4 white hydrogens, 1, 2, 3, 4. But now mathematically, 2 times 2 is 4 white hydrogens. And then 4 red oxygens. You have these 2 over here, and then those 2 over there, 2 times 1. And again, you can count them up, 1, 2, 3, 4. But typically, we're not drawing structures over and over again. We're kind of taking inventory in this kind of a T-chart fashion. So here's an example that I've done for quite some time. So here are my color-coded circles. And here's the inventory. So you have 1 magnesium coming in, 1 chlorine coming in, 1 hydrogen coming in. And on the other side of things, you have 2 hydrogens. That's what this 2 means. So 2 white circles. So there's the number 2 for next to the letter H for hydrogen. 1 red magnesium, and then 2 chlorine atoms or chloride ions, but atoms are kind of the way to go here because it actually doesn't matter if it's an atom or an ion. We just need it to be chlorine. And so here's the 2 teal chlorines versus the 1 teal chlorines. So this is unbalanced, unlike the prior example. So the magnesium 1 in, 1 out is great, but the chlorine and the hydrogen, you can't just create atoms. So these are that would violate the law of conservation of mass, law of conservation of matter. And so we need to not change the formula of a properly crisscrossed magnesium chloride, can't change the formula of a diatomic hydrogen, can't change the formula of hydrochloric acid. We need to change how many there are. And that's where these coefficients come into play. So as well as magnesium is good, I don't have enough hydrogens, I don't have enough chlorines going into the reaction. And the only way to get more hydrogens and chlorines into the reaction is by having more HCl. So this is where like the guessing and the checking comes into play. Now I put a number 2 there because I need 2 total chlorines. I need 2 total H's. So that 2 coefficient brings in another teal chlorine atom, another white hydrogen atom, or another hydrochloric acid molecule. And now I'm going to update my numbers. I no longer have 1. Now I distribute that 2 hydrogens, 2 chlorines. And so there we go. Okay, and so moving on to our next, well, I'm sorry, let's go ahead and check. 2 chlorines in, 2 chlorines out, that is great. 2 hydrogens in, 2 hydrogens out, that's also great as well. So this is a balanced chemical equation. So here's another one, a bit simpler. Or I guess it's all the same. So there's the T chart. Again, take some inventory. Sodiums are great, but the chlorine not so much, right? So I'm going to have to do something about that. I need new chlorine, and I can't just change the properly crisscrossed sodium chloride. So I'm going to bring in another chlorine atom by putting a coefficient 2 up there. And so in it comes. Update those numbers. Now I have 2 yellows, 2 yellow sodiums, 2 green chlorines, and now it's not balanced anymore because now I've had to mess up my sodium. It was balanced, now it's not anymore. So now I need to bring in another, I'm sorry, that one's checked. So now I need to bring in another sodium atom to update the 1 to a 2, and now it's balanced. And so I'm going to write this in. Give me a moment. So this is now a 2. There's 2 sodiums. Still only 1 diatomic chlorine, and now 2 sodium chlorides. 1 sodium chloride, 2 sodium chloride, 1 sodium, 2 sodiums. And so it does take some bit of a back and forth. So you can think of it as a challenge. That's probably your best bet. It's a fun challenge. And there's no clean, perfect process that's going to make this work. Sometimes it'll go by quickly, sometimes not so much. Embrace the challenge. All right, so let me scroll over. There's my balanced chemical equation there. Here's another one here. This is the combustion of propane we use for our propane grills. So here comes in the pictures. Again, fairly complex. 8 green circles. This time I switch up the colors. 3 white carbons. There's 1 white carbon coming out. So we need to take inventory for such things. So we have carbon, we have hydrogen, and we have oxygen. And we're starting this out with 3 carbons, 8 hydrogens, 2 oxygens. We're starting this out with 1 carbon on the product side, 2 on the 2 hydrogens on the product side, and then if you're counting up the reds, 1, 2, 3, in case it's 2 plus 1, 3 oxygens over there. So that's not good enough. It's not balanced yet. So what do? You have to change these numbers. We need coefficients to make this balanced. There's not just this magic way to go about this. I tend to work from the left to the right, which means I'm going to go after carbon first. So I'm going to bring in 2 more carbon atoms to give me a 3 total. And now I'm going to update my number. So now I have 3 carbons. You can count the 3 whites. So that's carbons. Now I need to update my oxygen. So now it's 3 times 2 is 6. And then plus the 1 over there. So that gives me 7 oxygen atoms. And so that's a good start. So again, I tend to work left to right. So I'm going to now focus on the hydrogen over here. I have 8 coming in and only 2 coming out. So I need some more hydrogens. And the only place they come from is the water. So how many am I going to add? Well, I want to have 8 little green circles. And so if I put 4, let's do the math. Now I have 4 times 2, 8 green circles. But I also have to update my oxygens because it does distribute. So now I have 4 oxygens there. In terms of the red circles, 4 oxygens there and 6 oxygens there for a grand total of 10 oxygens. And so I'm closer. My carbon is great. My hydrogen's great, but my oxygen not so much. And so I have 10 coming out, so I need 10 coming in. So I need to bring in some there. So what times 2 is 10? The answer is 5. So I'm going to bring in 5 oxygens, and now I can update my numbers to 10. Now I have 10 oxygens in, 10 oxygens out. I've now satisfied the octet rule. So it takes some back and forth. It takes some things. Now this does have a blank here. We don't have any blanks. They're implied to be 1, but for edge elastic's sake and for my sake, go ahead and put the 1 into play. And there it is there. So let's do some more problems without kind of the color-coded circles and actually just work on that T-chart. So separate your products from reactants. And so there's only 2. I went a little bit faster, but that's okay. There's only 2 elements here, a P and an O, and a P and an O. So you list the P and O in the center, and then you notice there's 4. Let me get my laser pointer back. You see there's 4 phosphorus, so there's the 4 phosphorus coming in, and there's only 2 phosphorus coming out. 2 oxygens in, 3 oxygens out. And so I need to change something. So I'm going to put a 2 there. Now, why am I going to put a 2 there? Well, again, I work left to right. And so 4 phosphorus coming in, I need 4 phosphorus to come out. So I need a 2 times 2 to give me a distribution, not only to the phosphorus, but also to the oxygen. But again, I can't separate it any other way. So now I can go ahead and change this 2 and the 3 into a 4 and a 6, because 2 times 2 is 4 and 2 times 3 is 6. So my phosphorus is good and great. Now I need to do something about the oxygens. I have 6 coming out and only 2 coming in. So I need a number here that is something times 2 is 6. And that number is 3. And so that's going to distribute to the 2. 3 times 2 is 6. So that 2 goes away, pops up to 6. And now I have balanced this equation. And again, we should have the number 1 written here for the P4. Another example. Iron making rust. So we need to track down all of the elements we have. Again, there's only 2 here, iron and oxygen. Now we start taking inventory. There's 1 iron on the left. There's 2 iron on the left, on the right, 2 irons on the right. 2 oxygens on the left. 3 oxygens on the right. And now we're ready to balance. So again, do you want to balance the oxygen first or the iron first? The key thing is you have to focus on 1 atom at a time. I tend to work left to right. So there's the 1 iron there, 2 irons coming out. So I need different numbers here. Or you can focus on the oxygen, which you're welcome to do as well. So because I could work left to right, I could also work right to left. So I have this oxygen 2 and 3 coming out. I need a common multiple. Least common multiple of 2 and 3 is 6. So 2s and 3s don't go into each other. So I need a common multiple to bring the 2 and the 3 together. So I put the 2 over here, and I'll show you why in a couple of moments. I need to distribute that 2 to the iron. So the 2 becomes a different number, and the oxygen is going to become a different number. And so now I end up with a 4 and a 6, because now we have 2 Fe2s, so 2 times 2 is 4, 2 times 3 is 6. So now I have the 4 and 6 in the back, and now we can focus on the oxygen on the left-hand side. And so now I need 6 of them. So the 3 times 2 gives me the 6 that I needed. And now we can focus on the lone iron out here. I have 4 going out, so I need 4 going in. And the coefficient of 4 is going to help me do that. Let's work on a different problem here. So this problem has parentheses to it. So the parentheses is just another thing for distribution. And so specifically that 3 distributes to the 4 for the 4 oxygens and also the 1 sulfur in there. So to write it a different way, it doesn't quite reach the aluminum that's outside of the parentheses, on the left-hand side of the parentheses. So it just goes within the parentheses. So 3 SO4s means S3O12. And again, the aluminum 2 stays put. Now I'm ready to take my inventory. Some people write that out, Al2, 12. Some people don't. That's okay. That's up to you. But now we're going to keep track of all of the elements we have in this little T chart. So I have aluminums, I have bromines, I have potassiums, I have sulfur, and I have oxygen. Now I'm going to take my inventory. I have 1 aluminum coming in, 2 aluminums coming out, 3 bromines coming in, 1 bromine coming out. There it is. I missed it. 2 potassiums coming in, 1 potassium coming out, 1 sulfur coming in. And now how many sulfurs coming out? These 3 here. And now I have these 4 oxygens over here, and then these 12 oxygens over there. So we have some double-digit numbers here. So again, just kind of focus on one element at a time. You could work right to left. You could go alphabetical, I guess. I tend to just focus left to right. And so I have 1 aluminum in, 2 aluminums out. So I need more aluminums to come in here. How many more? Well, 1 more coming in, but that's 2 total. So I put a 2 there. And now I need to update not only my aluminum numbers, but also my bromine numbers. So 2 times 3 is 6. Now I'm going to, again, working left to right. Now I have 6 bromines in. I only have 1 bromine coming out. So I need 6 total. So I'm going to put a 6 there, because that 6 is going to go to the potassium and the bromine, those coefficients. So now I update my numbers. I no longer have 1 bromine, I have 6. I no longer have 1 potassium, I have 6. And now I'm going to keep going. Again, focusing left to right. Aluminum's check, bromine check, potassium. So I have 2 potassiums going in and 6 potassiums going out. So what times 2 is 6? The answer to that is 3. And so when I'm going to distribute, 3 times 2 is 6 bromines, 3 times 1 is 3 sulfurs, and 3 times 4 is 12 oxygens. And now we have balanced this equation. Again, I do want the number 1 over here, no blank spaces. And so here is another one. This is the methane again. So I'm actually going to skip this one because we did this at the very beginning. So let me scroll on through. But this way it looks a bit neater. But I am going to scroll through this one since this was on the title slide, although you can kind of pause along and play along with this. Now I'm going to go to a little bit of a trickier one. I wanted to kind of show you what this one looks like. And so this is ethane. So there's my inventory of my list of elements. Now I'm going to fill it in. 2 carbons on the left, 1 carbon on the right, 6 hydrogens on the left, 2 hydrogens on the right, 2 oxygens on the left, 3 oxygens on the right. So I'm kind of there. So I'm still going to work left to right, 2 carbons in, 1 carbon out. So I need 2 to come in. Let me get my laser pointer again, excuse me. And there we go. And so 2 carbons going, 2 coefficient gives me not only 2 carbons, but 4 oxygens, plus this one over here, which will make the 5. So this 2 distributes. So carbon is good, hydrogen not so much, and so I'm going to go ahead and put the 3 over there. And now I'm going to distribute the 3 to the hydrogen. So get rid of the 2, pop up a 6. And now what about the oxygen? So this plus sign is literally a plus sign. So I have these 4 oxygens over here and these 3 oxygens over there. 4 plus 3 is indeed 7, so I'm going to go ahead and put that 7 there. Now I kind of run into an issue. Carbon's good, hydrogen's good, oxygen not so much, 2 to 7. And that 2 doesn't go evenly into 7. 7 doesn't go evenly into 2. So what do? Well, take a moment and do things unevenly. So what number do I need to multiply by 2 to get 7? So go back to your decimals, you get the answer 3.5. And so while that's true, that's a good start. There is a rule that we can't have fractions in the balance equations. And so you can Google it, you'll see it up there, but for the most part, it's supposed to have whole numbers. So what do? Well, to get rid of a half, you double it. So we have 3.5. We need to double not only this oxygen 3.5, but everything. And so I'm going to double it all. So what was a 1 becomes a 2. What was a 3.5 becomes a 7. What was a 2 becomes a 4, and what was a 3 becomes a 6. And now I'm not going to update my number because all I did was double everything, but you certainly can update it, and I missed a page there. And so I'm going to go ahead and let this be our last one so you can check this out. 2 times 2 is 4, 2 times 6 is 12, 7 times 2 is 14. On the other side, 4 times 1 is 4, the hydrogen 6 times 2 is 12, and the oxygens 4 times 2 is 8, 6 times 1 is 6, so 8 plus 6 is 14. So it is balanced, but we just needed to have a whole number here instead of a decimal there. And the next one is a similar way. So I'm going to actually skip all the way ahead to the point where I need the decimal. Now, not all combustion reactions are going to need decimals. In fact, it's pretty uncommon. What you have to have happen is this over here has to be divided by 2 and then be odd. And then even that, there's plenty of exceptions for that. But here we are again at 6.5. And so, because 6.5 times 2 is 13. But again, we can't have fractions up there. And so, instead, we're going to move this forward and double everything. So the 1 becomes a 2, the 6.5 becomes 13, the 4 becomes 8, and the 5 becomes 10. So it takes some practice. It either sounds impossible while you listen or sounds easy while you listen, but when you dive into the practice problems, that's where it's going to make the most sense. So thank you for your time. Remember, chemistry is everywhere.